everyone. Since it's 2:03, it's time to start the show. So we will start off with formative assessment number 5, which I looked at this morning. Thank you everyone for getting it done on time. Another perfect score with respect to attendance for this class. So first question was about quantile regression. For what kind of outcomes or situations would you want to do this technique of quantile regression? There's sort of a, in case of emergency, open versus a deliberate choice. So what is sort of the unfortunate aspect of data that quantile regression can help you address? Like a data problem. Outliers, yeah. So how does it help you address outliers? Yeah, we're going to predict the median instead, which is the middleist number. Outliers do not affect the median. Outliers affect the mean. So it's a better estimate of central tendency that's more robust to outliers. That way you don't have to make arbitrary decisions about which ones to include, assuming that they're all valid observations, of course. You shouldn't include data that are clearly not possible. Several of you gave really good examples about research questions that it could answer. A few of you told me about low birth weight as an example. Anybody here who gave me that example? There were 2 or 3 of you. That was you? Okay, tell us about it.
For quantile regression, I don't remember why.
Okay. Fair enough. I think the intent was that if you're trying to predict the birth weight of babies, you know, babies obviously vary in how big they are when they come out or were taken out, as were the case for me. And typically that variation is not of interest unless it's low birth weight, which is a marker for all kinds of bad things, right? Clinical people, is that a good way to summarize it? So being disproportionately small, I think, is potentially related to further bad outcomes. And so being able to predict birth weight differentially within the lower section of the distribution would be a way to answer a question about what predicts low birth weight specifically, not just what predicts birth weight variability. What I've seen people do to answer that question is dichotomize birth weight into some sort of arbitrary low versus not low. And that requires essentially collapsing the information, limiting the amount of variability, and thus limiting your power. So to the extent that you don't have to avoid those sorts of artificial collapses, that's a better strategy. So I like that one. There were a couple others in an analogous vein. If you're trying to do some sort of professional development for teachers or learning interventions for children, generally those approaches are targeting the lower end of the distribution where they have room to make growth and improvement. So an analysis that focuses on what predicts differences in the lower part of the distribution would be useful for that. It might also be the opposite. So let's say that you want to predict achievement within gifted children. So what determines differences at the high end of the distribution? That might be a research question for folks. So beyond just this can be used to address messy data filled with outliers, this can be used to address different types of questions with respect to which side of the distribution are you interested in predicting, and do the same relationships hold at the upper end of the distribution as at the middle, as at the lower end. So like I said, quantile regression is one of those things I wish I had known about sooner, because I feel like it's more useful. And in terms of the lift, like there's no link function, right? There's no alternative distributions. It's just a regular regression model, but predicting a different spot on the distribution than a mean. So it's relatively straightforward relative to the other things that we've talked about. So any other thoughts or questions on that? Happy garbage day. You're like, yeah, I'm not here for that, Lisa. 3 weeks left? Are we here for that? Yes, I know how you all feel, and just, it's finite. In 4 weeks, this will all be over. Better or worse, it will be over. So there will be like things checked off your list that never, like they don't come back. Then you have the closure of the semester. And then you can use the summer to do other things, right? We all want to be productive over the summer. And by August, I'm like, wasn't I going to be productive? I forgot. So maybe that's just me. I always have these lofty goals and hit like 1/10 of them. Dependency. What does it mean to have dependency or to have non-independent data, as I've seen before? So what does that word mean, just dependency? Yeah, like codependency is considered a bad thing, right? That phrase. And when statisticians talk about having dependency in your data, that's sort of a bad thing because it means that your standard independent samples techniques are not going to be applicable. But for some people, dependency is the whole point of their research design. So what would be an example of that? When is dependency useful? Question. Yeah, longitudinal. You have to be able to see the common trend across multiple observations so that you can characterize an individual's trajectory of change over time. Dependency for the win in that case. What if you're interested in educational settings? What kind of dependency might arise there?
If a student has the same teacher for like a couple of years, or is even just in the same school for a couple of years.
Yeah, what school the kids go to, what teachers they have, what cohort they're part of if it's not a, a strict teacher-teacher thing. To the extent that you are going through a common set of experiences or procedures, people from the same group are going to be related. That's dependency. Dependency is the idea of the residuals from different people or different observations being correlated because of some common tendency. The good news is that everything that you've learned so far in terms of how to fit standard general linear models, how to fit generalized linear models, all of those things can be extended for sampling designs that have dependency. The way to extend them is to add what are known as random effects in most cases. We'll talk a little bit about that today, but that's where the coursework on mixed effects models or multi-level models would help you have a lot more choices for dealing with dependency. Other ones you can think of? I have longitudinal and clustered. How about family research? Does anybody do family research in here? No? Okay, fine. Dyadic data, that's another one. Family data where you have siblings and parents and things like that, that would be another type of data that has dependency. Last but not least, only 3 questions this time. What's the difference between balanced and unbalanced in terms of multivariate sampling designs? And which one are we doing this semester? We're doing balance, that is right. I don't want to get your hopes up, like you're going to learn about everything multivariate in 3 weeks, because that's not going to happen. What does balanced mean?
Means that they have same potential, occasions, situations,
Yep.
the same.
Yes, exactly. Same potential types of observations. So if it's a longitudinal study and you have like pre-test, post-test, everybody was measured at the exact same time. There's no like time 1.5, time 2.3. If it is a psychometric design where people are responding to items or stimuli, it's the same distinct items. If it is a repeated measure study where you're seeing performance under different conditions, everybody has the same potential set of distinct conditions. Unbalanced would be like studies where people beep you on your phone and ask you to answer questions at random intervals. Items that are generated randomly, so there's like not a fixed item pool. Those are the 2 main ones that I can think of beyond clustered data. So when you have individuals in groups, the group is the unit that's being measured multivariately in that case, and the data would be unbalanced if each group has a different number of people, which is like always the case. That's usually how it goes. I had some questions on that about the intersection between balanced and unbalanced versus missing data. So that's a different concern. You can have a balanced sampling design that has incomplete data. So like everyone could have seen conditions A, B, and C, but they only saw A and B for some people. That's still balanced because the set of possibility is the same. It's just incomplete. So another way to think about unbalanced is that it's by definition incomplete to some extent because there's no common set that people come back to. If we are using analyses that involve least squares estimation, ordinary least squares, then balanced data has to be complete. So if you go with your classic multivariate analysis of variance or anything like that, repeated measures ANOVA, if you're using least squares, then you cannot have incomplete data. Everybody has to have everything to be included. The use of likelihood estimation instead allows you to retain partial data. You can still use whichever occasions or conditions are complete. You don't have to kick out the whole person necessarily. The exception to that is on the predictor side. So if you have a repeated measure study where you're looking at performance in conditions A, B, and C, and you collect, personality measures at baseline or something, if somebody didn't complete the baseline observation and you don't have the personality measures for them, you don't have it for their A score, their B score, and their C score. They're gone. Then it's list-wise deletion. So missing data on predictors is a way bigger deal because there's no way to come back from that. You have to do something else. What else you can do, one of the options that we'll talk about when we get into path models, I think starting next week, is bringing the predictor into the likelihood, which means you trick the program into thinking it's an outcome, which means you can have missing data under certain assumptions. So we'll see that next week as one potential solution. Multiple imputation is another potential solution, and Bayesian analysis is yet another. I think those were the questions that I saw, was about incomplete versus balanced. Any other questions on that? And a few of you remarked that I told you that pre-test, post-test designs were not ideal, and you were right about that. So I wanted to clarify. Here's the reason. Actually, let me pull up a picture real quick, because a picture is worth 1,000 Lisa words. Un momento. Yellow, this is my longitudinal class. All my PowerPoints are color-coded, so that way I know what I'm talking about. You guys are orange. This is yellow. Okay, so in this class, let me just show you two quick slides here. I have an example of a pre-test, post-test design where I have a control group and a treatment group, and these are the cell means. So the design was such that we expect that everybody grows to some extent, so the control group grew. We hope that the treatment group would grow more from pre-test to post-test. And the interaction between group and change is how we test whether the intervention was effective. Relative to control, did treatment change more? Cool. So here are the two choices then in terms of how we think about variability from that type of design. You can ignore the letters for now and just look at the shapes. Either it is the case that everybody changes the same, but there's some degree of individual and time-specific error around those trajectories, or everybody changes differently with no error whatsoever. If you have a pre-test, post-test design, and you give each person 2 points, and you have a line between the 2 points, that line has to fit perfectly. So either there are individual differences in change measured without error, or there's only differences in intercept. Change is the same and measured with error. A two-occasion design cannot differentiate between these two possibilities. That's the problem. In order to have an individual specific change and error with which to judge its significance, you need 3 points. So two-occasion change is the bare minimum to look at change. It's not a good idea. You have very little power because of this non-differentiation between change and error. So just a little bit of elaboration about that point. I do not recommend pre-test, post-test. When people come to me for advice about how to plan longitudinal studies, they say, how many occasions do you need? And you know what I say? More. Whatever you were thinking, it's more. They're like, but it's hard to get people to come back. I know, but you need more. There's only a few of you for whom I would say, like, you need less. Some of you are in the position of being overpowered because you have giant data sets filled with people. You will have the opposite problem. But for longitudinal data, it is hard to get people to come back and do the same measures repeatedly. I get it. But pre-test, post-test is usually not a good strategy. So there's today's rant about that. Longitudinal is coming back a year from the fall. So fall 24 is when the longitudinal sequence will come back, in case you want to play with that. This fall is the cluster data instead. All right, I think we finished all the questions then. Anything else that you wanted to go over or that I forgot to mention with respect to these? I did update grades this morning too, so if you're feeling anxious about where you stand, you can log into the portal and see your scores. Nobody who has finished everything should be feeling anxious, I'll tell you that. It's all going fine. There will likely be an opportunity for extra credit If you complete course evaluations, I will tell you that too, because I am shameless in trying to get my evaluation completion rate to be as high as possible. That's my goal. That way we have a representative sample. And I will bribe you. Well, some would say it's a bribe. I would say I'm going to compensate you for the time it took to provide a thoughtful evaluation. That's what I think. In the same way that I will compensate you with 2 points for filling out this quiz. Same difference. All right, let's see. It's Tuesday, which means I say, do you remember what happened last week? What were we talking about? I've got a slide here to jog our memory.
Tricking univariate into multivariate analysis.
Yeah, we are. So when would we need to do a multivariate analysis?
If you've got that wide, or, no, if you've got the long structure, right?
We need a long structure in order to do multivariate analysis in univariate software. That is true, but my question was a little bit back from that. Like,
Okay.
why would we do this? When would we do this?
There's like 2 outcomes we're interested
If I have more than one outcome per person, is one situation, so a repeated measures type of design. Another one would be hypotheses involving mediation. So mediation is a big damn deal in a lot of different fields. The idea that you have X that causes this mediator, and the mediator causes Y, and that's the reason why X and Y were related. It's because of this other pathway. In order to do an analysis like that, we have to allow the mediator variable to be both an outcome with respect to X and a predictor with respect to Y at the same time. There are ways to separate that out into distinct analyses, but those are suboptimal relative to doing it all at once. So that's another instance in which we would want to do multivariate. A third, which we will talk about, I think, later today, maybe Thursday, is the idea of testing differences in effect size across outcomes. So if you have multiple ways of measuring performance, one of your questions might be, does the effect of this predictor, is it stronger in predicting this outcome than that one? So questions about differential prediction have to be answered in models that have all the outcomes being put together at the same time. So then our test, our trick, beyond just restructuring the data here, is making sure the software understands the multivariate structure of the data, saying, hey, can you make sure that the observations that come from the same sampling unit get to have this additional religious residual relationship? There's no church up in here. It might feel like you're having a religious conversion when you finally get this to work, but that's not my intent. We have to make sure the software understands residual correlation and to put it in there and figure out which kind we need with respect to different potential patterns. If you only have 2 or 3 outcomes, that's pretty straightforward. It gets more complicated when you have different types of sampling designs. So yes, this is an important concept in terms of data management, but also in terms of analyses using anything involving likelihood estimation in univariate software. We have to restructure. So the type of data structure in which it's 1 row per sampling unit. So I'm saying that deliberately because for some of you, sampling units are people. For some of you, it's businesses. For some of you, it's schools. For some of you, it's teachers. But the thing that's being measured repeatedly is your sampling unit. In a wide data structure, that entity has 1 row, and every different observation for them, whether it's a predictor or an outcome, is in a different column. So conceptually, like we might think of this outcome as Y, and it's being measured at time 1 and time 2. In order to use univariate software in which we are only able to predict 1 column at a time, we have to reshape this, or stack it is what I tend to say, into a structure in which it's 1 row per outcome per sampling unit. So because there's 2 columns, each person now gets 2 rows. So it's like a per person transpose here. If I had Y time 1, time 2, time 3, how many rows would I have over here for per person? Not a trick. If I have time 1, time 2, time 3, now how many rows do I need over here? 3. Yes, I promised you there'd be no trick questions towards the end of the semester. So yeah, you can get fairly large data fairly quickly. The key thing here is that we need to create new variables that keep track of which outcome was which. So I have time 1 and time 2 matching the labels here. In order to put that in an analysis as a predictor, I need to convert it into a centered variable where something is the 0 point. So I have x here as the predictor that would go into the model instead. So if I have that type of structure where I have 3 people and 2 outcomes, then the trick to it is making sure that the little pockets here, these little blue squares, known as a block diagonal structure, that the software understands that we have 2 different kinds of outcomes, and for the same person, they get to have a covariance. So we're assuming that the same variance and covariance parameters hold across people. We're just allowing the residuals from the same person to be correlated. And if you only have 2 different outcomes, this is what I do, and that would be the end. We talked about this idea of multivariate likelihood very briefly. In terms of the underlying machinery of how we figure out which model parameters are relatively best that make the data the tallest, we're going to evaluate the height of a person's set of outcomes together. So it's a multidimensional sort of mountain rather than just one value for each person. And then we talked about a little bit about potential choices for what the patterns could be. Let me pull up this slide here because I think that's the easiest. So this pattern right here, given by the subscripts very important in telling a story here. 1, 2, 3. 3 different symbols here. That means that what we're saying is that the variance of the first outcome gets to be whatever it wants, the variance of the second outcome gets to be whatever it wants, and so does the third. So this pattern is what's known as heterogeneous variances. We're not assuming that the outcomes have the same leftover variability, and in most cases that's appropriate. Then we have the covariances. So this is the relationship between outcome 1 and outcome 2 with respect to the leftover residuals. We're in general linear model land for right now. This is the one between 1 and 3, and this is 2 and 3. And the fact that I'm using different symbols for all 3 of these means that we're not assuming they're the same either. So whenever you just let it be whatever it wants without constraints, that is called unstructured. Another word that means the same thing is saturated. So basically you've spent all your degrees of freedom. You're not making any constraints to say, let it be what it wants. Pros, this is the right answer. Like there's not going to be a better answer than this because you're letting it do whatever it wants. Cons, how many of these can you possibly estimate? So for 2 or 3, this is fine. But the number of different parameters you would need grows exponentially with the number of different outcomes. So that's the downside to that. So alternatives to this, by the way, you can force these variances to be the same or different. That's homogeneous versus heterogeneous variance. And you can force the correlations that create these covariances to be the same or different. Those are really the only choices that would make sense. So I'm not going to emphasize that too much in this class other than to say that these are some choices that you have. There's 37 other ones for different kinds of data. And I have a whole nother class about all the other choices in the longitudinal class that we will talk about. But for multivariate data of a generic type, these are the only 3 options that really make sense. Okay. I think we ended here, and then I lost my will to live. Does that sound about right? My will to teach, I should say. So assessing model fit. So broadly construed, what we're talking about that distinguishes this unit from the previous ones is concerns about the model for the variance. What type of correlation pattern do we have? Are they all the same or are they different? What type of variance pattern? Are they all the same or all different? And just as we saw in the generalized models where we have things that are related to each other, where there's one is a subset of the others, any type of concern about what belongs in your model for the variance is a likelihood ratio test. If it's a nested model, or AIC and BIC if it's not. So we have to usually do something extra to answer questions about these things. In contrast, fixed effects, things in the model for the means, we can stare at the p-values that show up in the output. Those are called univariate wald tests. If you lump slopes together to create an omnibus test of multiple slopes, that's a multivariate version of the test. We can always do that regardless of what kind of model we're using. And I think this was where we left off. So how are we doing so far? Can I tell you a story? Well, I'm going to, so it's a sort of rhetorical question, but I feel like we could use a story maybe. So this weekend, I took my 8-year-old son out shopping for new shoes because his had holes in it. You know, kids are really hard on their shoes. And he selected his first pair of shoes with shoelaces. Because it's like there's Velcro is everywhere, right? And so I've been able to avoid this problem, but his feet are like size 4, which is in like heading into like big boy sizes where all the shoes that have laces. And he picked out these black shoes with this neon green lining and shoelaces, and they're really cool, and he's very excited about them. And I was like, do you know how to tie your shoes? No. Oh, God. So, like, I have a PhD, right? I've been doing this for, I'm 20 years, right? I was humbled by the fact that I could not teach my son to tie his shoes. It did not go well. Tips?
I used a YouTube video.
You used YouTube. No, I thought about that. I was like, I should Google this.
Rewind it and I didn't have to teach him. Sometimes kids just don't want to be taught by their parents.
Yes.
I don't know what it is, but like YouTube.
No, I thought about that because I was like, I need to outsource this because like this is a skill set I don't have. And then I thought, oh, come on. You can't teach your own kid to tie his shoes. What kind of mother are you? Spoiler, she did not teach her own kid to tie his shoes. She just managed to make him angry. And then just went downhill from there. And in that moment where he's like crying and frustrated and I'm trying to walk him off the ledge, I'm not going to wear my new shoes. I hate this. I thought, God, if I could only be teaching about matrices or something, right? Like this is so much easier than that. And I had that, and I thought, I bet I could teach him what a V matrix is more easily than I can teach him how to tie his shoes. And I have great respect for all the preschool and kindergarten teachers, and apparently at one point that was a lesson in his preschool class, and we never had the shoes to support the lesson. So, yeah. Well, I'll let you know. We're going to work on it again tonight. It's going to be like a daily thing, I think, where we try. But any tips on how to do this or suggestions for YouTube videos would be greatly appreciated. I am humbled by my lack of capability. But I can do this. And you're like, can you teach us how to tie our shoes instead? Because we'd prefer that. But no. So
Teach him about the V matrix.
I will try. I think I would have a better chance at it is the point. Like I just realized like being a teacher in one thing does not translate to all the things that need to be taught, especially when it's your own child. So yeah, I can't imagine, of course, given who his dad and I are, we actually met like in this field. So we're both quantitative methodologists. He kind of doesn't have a choice. Like he's going to get into this at some point. So, but probably not this level of specificity. So I was humbled.
He's just going to do qualitative methods throughout his life. He's like
Yeah.
never going to touch.
That's how he's going to rebel against his
Yeah.
parents, is become a qualitative researcher, yeah. Like when the hippie child has, Alex P. Keaton or whatever, Family Ties reference, probably dating myself, but yeah. Children want to do what their parents are not, is what I understand. But he's still 8, which means most of the time he doesn't hate us yet. Those days are coming, I understand, but not yet. So, compound symmetry, anyone? So we talked a little bit about the patterns here, and these are the words that go along with the patterns of possibility. So there is unstructured as one choice. All the variances and covariances get to be what they want. If you simplify that and say, no, the variances can be what they want, but I want the correlations to stay the same, that's compound symmetry heterogeneous. And then compound symmetry without the heterogeneous is no, make everything the same. And so this is a term that you may have used or heard in learning about repeated measures ANOVA, because the univariate version of repeated measures ANOVA is this model under the hood. But this has a direct translation into another term that I want you to have heard about, which is the idea of a random intercept. So that's where I want to start with this. So this pattern right here, what I'm looking at is the matrix of residual variances and covariances across outcomes from the same person. That's what we have here. And the same thing is on the diagonal here. These are the variances. The same thing is on the off diagonal. These are the covariances. So no matter how many outcomes you have, there's only 2 things you have to figure out. The CS thing and the sigma squared sub E thing, which is our residual variance. Another way of describing this same thing, though, is with this thing called U. Did you have a question?
Yeah,
Please.
just like y for 3 outcomes
Y for 3 outcomes. What was the rest of it?
Why, I'm just like, why we chose this compound symmetry? We have 3 options, right?
Yes. So if you pick this one, there's a direct translation to another way of setting it up. And where I'm going is that the other way of setting it up is the way you have to do it if you have a generalized model. This possibility of having separate or not variances and separate or not covariances, that is a general linear model thing, because that's the only kind of model that has a separately estimated variance that's assumed to be constant across people. We're allowing different ones potentially, if you pick the backwards. If you pick the unstructured, we're allowing different ones across people, but it's still the same idea as the normal distribution has a separate variance. None of the other ones do. So this idea, just let it be correlated, duh. That's only applicable for one tiny kind of model. Your standard linear regression kind of model when extended for multiple outcomes. And where are we? There we go. This one. So this U thing. The same pattern of CS plus variance shows up down here with a different set of notation. Another way that people talk about this compound symmetry parameter that introduces correlation or covariance across outcomes from the same person is that it comes from a random intercept. So what is this thing, this U? That's what I want to show you very briefly. So another way of thinking about this particular type of correlation pattern that says all the outcomes have the same leftover variance and all the outcomes have the same leftover covariance is written this way. So univariate, meaning when I have an outcome for one outcome per person, we're used to seeing models that look like this. So the red part here is the fixed effects. We have a fixed intercept, effects of our predictors, yada, yada, yada. And then we have E here in the normal distribution models, at least when we're doing conditional normal. What I'm talking about is separating out what we used to just call error into 2 different kinds. So the multivariate notation picks up a T, because in this example I'm saying it's per occasion as my multivariate observation. And the U only has an I, but the E has an I and a T. So what that means is that each person gets one of these blue U things, whereas each distinct outcome and person gets one of these E's. This U thing is called a random intercept. It goes with the fixed intercept because together what these do is allow each person to have their own intercept. So the fixed intercept and the random intercept together create a variable that allows each person to have their own starting point, i.e. controlling for individual differences. That's the idea here. Visually, let's say that I have an average line for the sample across 5 outcomes, occasions here that looks like this. So there's no change on average. This might be a study where we're watching people fluctuate around their averages rather than have systematic change. And if I look at the distance between this purple person's residual at time 1, 2, 3, 4, 5, there's something in common here. This person is below the mean at every occasion. Sometimes they're more below than usual, but they're below. So the fact that this person is consistently lower than everyone else creates a kind of dependency. Well, let's fix it. What if we allow them to have a different starting point that takes into account their common tendency exhibited across all their outcomes, and it's a deviation from where the rest of everybody is to get down to where their mean across time would be. So UIO in this class, it's UOI in my other classes, that is called a random intercept. It is the idea that each person needs their own starting point that operates across all the outcomes you've collected. It's what's in common to this person. I'll say that a different way. UI is the idea of individual mean differences that show up across all the things you're asking them to do at every occasion and every condition for every outcome. So if we bring that into the model, what we have done is take the total leftover variability for each of my outcomes and carve it up into 2 pieces. How much of the discrepancy between what the sample average is and where this person is on their first outcome is due to which person it is, that's U, And then the deviation from this dotted line down to the actual data point is E, is the leftover part that's outcome specific. So we've taken what we would think of as just one source of variability and carve it up into two. How much of it is common because you're you? See, you. You're you. That's your mnemonic. How much of it is common because you're you, and that operates across all the outcomes? And how much of it is just because of what was going on at this occasion? Like relative to my PowerPoint drawing ability, this person was a little bit lower than they tend to be. The second time they were a little bit higher, a little bit lower, right on, and then a little bit higher. So we haven't introduced any kind of prediction. We're not explaining variance. We are simply allocating it for two different reasons. Some of the leftover variability is person-specific and it's common. Some of it is just occasion-specific or outcome-specific and it's not in common. So this is known as a random intercept model. This is the basis of the univariate approach for repeated measures ANOVA. And this is the starting point for most kinds of multivariate analyses that feature either balanced or unbalanced data. We want to know how much is in common versus how much is unique. I don't think I have it in here, but if you've heard the phrase intraclass correlation, does that phrase sound familiar? That's used in the context of reliability analyses as well as in longitudinal or clustered analyses. Intraclass correlation, roughly speaking, is how much of the total variability is due to you instead of E. That's what that means. So how much of it is due to the common part? So this is what it looks like if you're like, can I see the matrices? You know, said no one ever, but in case you're that person, this is what it would look like. So we're adding in this second part here that you have not seen up to this point. The idea that we have, each person potentially has their own set of individual specific terms in the model, an intercept to start with, and slopes later on. And that means that the model for the variance then has these two things in it. So U does the same thing as just letting your residuals be correlated. It's a workaround for situations in which you don't have that choice. So let's say that you have 3 count outcomes. Number of times that Lisa said shit while she tried to teach her son to do matrices, tie his shoes, or ride a bike, right? That's my count outcome. It's not going to be zero inflated, I'll tell you that much. What am I going to do in that case? I have a common tendency to say shit when I'm frustrated. That's my U, okay? But I don't have an E, right? Because if this is a count variable, I don't have a residual variance. I might have a stretchy factor, but that doesn't work the same. So this previous idea of just, can I let my E residuals be correlated and be done? Well, not if I don't have an E residual. So this is a workaround that does the same idea. U introduces a source of common correlation across the outcomes from the same person. And it's the building block of all more complex analyses that involve unbalanced data. So you can add this U thing to bring in correlated residuals, whether you have general or generalized, whether it's balanced or unbalanced, whether it's complete or incomplete, and so forth. How are we doing? Yeah, Ian is correct. Yeah, sideways thumbs at best is what I'm hoping for here. My guess is that if you were to take further coursework on random effects and then like rewatch this 2 years from now, you'd be like, oh, that's what she was talking about. So I'm just planting seeds here. How many of you have done path analyses before? No one? A little bit? Have you ever done a path analysis with a generalized outcome? Nope. Yeah, so true story. I published a paper in 2010 where I had 2 binary outcomes at the end of a path model. And I thought, well, these are binary outcomes. They should be related to each other. So I tried to add a correlation between them to my path model. And the software's like, no, you can't do that. They're binary. Okay, so I didn't do it. And I left it alone, and the paper got published. 7 years later or so, when I started teaching this class, I was like, hey, I could do that U trick. And my class example, one of the things you'll see probably the last week of class is what to do if you have a binary set of outcomes at the end of your path model. They need to be related somehow, but you can't do it via a covariance directly. What you can do is stick in a U thing, which amounts to a latent variable in SEM terms. So this trick is very common and very useful for a lot of situations, which is why I'm bringing it up. So all I want you to remember right now is that if you have generalized outcomes that are multivariate, you can't just let them be correlated. You got to do this trick involving random effects instead. So this is one kind of random effect. It is an intercept. Other kinds of random effects are known as random slopes. And in that case, what we would do is allow each person to have their own effect of a predictor. So right here in this model, I've got beta O1 and beta O2. These are mean differences between DVs A, B, and C as my reference. The fact that these betas don't have I subscripts means they're fixed, means they're constant. They're assumed to be the same for everybody. But do you think it's possible that some people might have more of a difference between their A outcome and their C outcome than other people? Sure, particularly if you manipulated it to be that way. Yeah, so then in order to answer that question, do some people, are they more affected by my manipulation across conditions? That's another kind of U that would go into the model, known as a random slope. Yes?
How does that work? Because this is making me think of just how you would set up coding for an interaction term. So how does that?
Great question. The question was, how does that work? Because it sounds like an interaction term. That's exactly what it is. But it's an interaction between a fixed effect and a random effect. So another way to think about this U thing is it's a main effective person. If you think of this as a factorial design. If I have 3 outcomes and I have 10 people, then these two, beta 0, 1, and beta 2, these are fixed effects that differentiate outcomes A, B, and C. So I have a main effective outcome type. Then I've got all 3 for my 10 people. U is the analog to a main effective person. The difference is that if I wanted to treat person as a fixed effect and I've got 10 people, I would need 9 dummy codes to control for which person is which. I would basically put in person ID as a predictor. Instead of 9 dummy codes, what I'm adding is this term, which implies a variability across people, and it's one thing, not 9. But more importantly, just allowing there to be variability but not say why allows you to then put predictors that say why. So why is it that this purple person is lower all the time? Well, what is it about their background, their characteristics, their personality, their resources, yada, 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 right? To the extent that you can predict why some people are higher or lower all the time, then that's a conclusion. So what you would end up doing is, more matrices. Yeah, this is where we were. A random slope would essentially be another U-type term. It would have the same number attached to it as the slopes, and it would also multiply like dVA by dVB. So then you'd have a person by condition interaction. Some people have different condition slopes, but the person part is random and not fixed. So this is solidly in multi-level modeling territory when we get to that point. Not to overwhelm you, but there's more to the story, point being. The U thing, though, is you'll see this in this class, which is why I wanted to set that up. And here's the matrices that show how it all gets put back together again. So, all right. Yeah, so I don't want to talk about this. I'm moving on. Here's the too bad you can't do this for generalized models slide. I'll show you what to do instead, which is path analysis. Okay, changing strategies. So how would I go about putting this in an analysis? I want to show you some choices. Yes?
Just want to clarify some points.
Yeah.
So what you just showed us that using is that to lead to the compound, what's that called? Compound symmetric.
Compound symmetry is the same thing as a random intercept only model.
Yeah, and they are only applied to general linear.
Compound symmetry only logically is possible for outcomes in which there is a separately estimated residual variance, so conditional normal outcomes. If you have count outcomes or binomial outcomes or something, then instead of compound symmetry, you can achieve the same effect by putting in this random intercept that divides whatever variability. Even in models where you don't have a separately estimated residual variance, you can add this thing to it.
Okay, so I will add this thing, but that won't lead to compound symmetry, right?
It's as close as you can get given a generalized outcome. So the E part is not the same, but the idea is that you're introducing a source of common covariance across all the person's outcomes that has to do with them, and it represents mean differences for them relative to other people. That's what U0 represents, regardless of what family you're in.
Okay, and what the metric looks like?
What-
will the metric looks like?
The metric? Which metric?
Like when you introduce this constant arrow, like among the person, but you don't have a separate residual.
Oh, yeah. So it would look like, I don't think, yeah. So it's not easy to summarize, but what you would say is that the way that you phrase the predicted outcome includes both the fixed effects and the random effects, and then there's some kind of conditional distribution left over. And the question is what that would look like is based on what type of model you have. So it's not easily summarized because in the same way, but it would be like this is conditionally a Poisson, or this is conditionally a negative binomial, or conditionally a binomial. After you include whatever random effects that you need that allow residuals, allow outcomes to be correlated from the same person, then you can pretend that the outcomes are actually independent because they're independent conditioning on the person random effects. So it's this same idea, by the way, for those of you who are like, does this talk about this in IRT or one of those classes? Yes, this is the same thing, conditional independence. After you control for a person's latent trait, which by the way is a U, then their outcomes, their item responses are independent. Same idea. So then we can get by with individual outcome-specific conditional distributions that don't have a multivariate structure because we've taken that and shoved it in the other part of the model, the U part. So this must tell you how bad the shoe tying went if this I thought would be easier. I'll send you an update later. All right. Yeah, I know. If I ever get him to tie his shoes correctly, I'll send you a picture, maybe even a video. We have to manage the frustration of both of us, because I'm frustrated with myself that I can't figure out a better way to teach this. But I did 2 bunny ears, and we just tied them, and that was the best I could do. Try to tie your own shoes slowly. You will forget how to do it. It's one of those like automated things that it's like, how do I do this? I just know how to do it. Believe it or not, eventually this stuff will feel like that too. No, don't give me that face. It will. It just takes 20 years of banging your head against your shoe before we get to that point. All right. So I want to talk to you about strategy, because there are many different ways to set up these multivariate models, and some may be more useful than others. And so I just want you to have seen examples of different ways to do this so that you can adopt them into your research as needed. So these are strategies that are especially useful for multivariate analyses, but not just those. Sometimes for univariate analyses involving a whole bunch of categorical predictors, I will do something analogous to these. So 2 different ways of setting up a model. The big difference is whether or not you keep your beta 0 general intercept or whether you don't. That's the big difference. The rest of what I have to say is a logical consequence of that distinction. So if the goal of your analysis is something like a repeated measures ANOVA type of design, where you've deliberately created different outcomes based on some kind of manipulation, like you have to do it this way in A and this way in B and this way in C, and the whole point of the analysis is to see how your manipulation creates differences in the outcomes, so how A differs from B differs from C, then a strategy in which you have a common intercept that will represent the reference outcome, up to you which one that is, but in common, will probably be most useful because everything that you'll get back is some kind of conditioned mean difference. In contrast, if you're interested in predicting each of your outcomes and you're thinking of them as sort of logically separate, so the example that I'm going to show you is a measure of attitudes collected for 3 people from the same type of family. We have moms, dads, and an adult child. So even though it's repeated on the family, the way that I'm thinking about that in my head is mom's attitudes and dad's attitudes and kids' attitudes. Well, in that case, phrasing it as, well, one of my people is the reference person and the other are the alternative persons is sort of weird, because I want to know what predicts mom answers and dad answers and kid answers as separate things. So the solution to that disconnect is to kick out the general intercept. The beta 0 is gone. And we replace it with dependent variables, the shortcut here for DV, outcome-specific intercepts instead. We allow each type of outcome to have its own intercept in the model, its own slopes in the model. This is directly analogous to what happens in path models. In path models, you have a separate outcome box, and you can have things predict your box, and they're separate boxes, and each box has its own intercept and its own parameters. I will note that this approach of predicting all of the outcomes is a better alternative than ANCOVA strategies where you're predicting, say, post-test, controlling for pre-test, or anything like that. I really don't like that type of analysis. I can give you an article to read that describes why. It's known as residualized change, but most people don't know the difference between change and residualized change, which is why it's a problem. So if you're interested in predicting differences, I would put both outcomes in the same model, because if you do that, you can predict outcome 1, you can predict outcome 2, and get the differences as a linear combination, or predict the outcome 2 and the differences and get 1 as a linear combination. You can get everything at the same time. So here is an instance in why we would want to do something like this, differences in predictor slopes. In this diagram, I have effect size as the line right here, the arrow, and I have the arbitrary line in the sand where the effect size crosses significance. Where this line in the sand is drawn depends on your sample size. So if you have a giant sample, then it's like clear over here, anything is going to be significant. If you have a small sample, it's going to be clear over here. So what if you have a separate set of analyses where you find a predictor is significant in predicting A, and it's significant in predicting B? Yay. Can you say that the extent to which it predicts A and B is different? Well, you'd be like, well, they're both significant, so no, but maybe they are. That's not the question. Whether each effect is different than 0 is not the same question as whether these effect sizes are different from each other. Different from each other requires a multivariate analysis where you explicitly look at these and the difference is a linear combination. Here's where it gets even trickier. Let's say that you do the same type of analysis, but this time your predictor does not predict outcome A, but it does significantly predict outcome B. Are those different results? On the face of it, you might say, well, yeah, one's significant and one's not, so that makes them different. Not necessarily. It's the same issue. We want to know what the difference in effect size is. So where I'm going is that for these 3 pieces of information for 2 outcomes, you can ask for 2 of them at the same time and get the third as a linear combination. Which 2 you get is up to you. The strategies that I want to show you are designed to either emphasize what happens for each separately, or one of them is the reference and the difference is a model parameter. Difference as a model parameter is more useful if you're in a repeated measure setting where differences are the thing you care about. What happens to each of them is more useful if you're thinking about these outcomes as like separate logical variables, like mom score, dad score, kid score would be in my example. So here are 2 different ways of fitting the same type of model. I'm using 3 outcomes in this case. So I have already gone through a process in describing this example where I have reshaped my data from wide to long. So I now have one variable that is called y. It's all in one column. And each person would have 3 rows, one for outcome A, B, and C. So I would have perhaps a categorical indicator variable as to which is which. That goes with it in the stacking process. And then I am also going to build 3 separate demi-coded predictors where it's 1 if it's that one and 0 otherwise. It sounds like this might be redundant, but it's not. So this would be the coding scheme in sort of generic language. So if I include a general intercept, then my fixed effects are going to refer to the difference of one of my dv's relative to the reference. If I have dv-specific intercepts, then I will end up getting a slope of a predictor per dv, and any differences have to be linear combinations. And this is analogous to how path models are phrased. So to try to be more concrete here, if you do this as a factor variable, it's the same premise. The code just looks a little bit different. I deliberately took this out of my examples this time to avoid confusion, but just know that this is potentially a shortcut. I'm not showing it to you on purpose so that you know what your parameters mean. So here's one type of model here. I'm calling this an empty model. Do you remember what an empty model used to be? What that word means? Just the expected mean with no predictors, right? That's what empty was. What if I told you this is also an empty model? Even though it looks like I've got predictors in here. The reason that I am calling it empty still is that the only variables that are included is indicator variables as to which outcome is which. So what this is allowing me to do is say that beta 0, 0 here is the intercept for my reference outcome, which is going to be C in this case, because that's when these dummy codes would be 0. The first slope is giving me the difference for how the A outcome differs from C, and the second slope is giving me B versus C instead. So I still call this empty because all I've done is allow a separate mean for each of my outcomes, and potentially a separate variance as well. So the three parameters that I get directly tell me the mean for the reference group, the difference for the alternative two groups. Does that sound familiar? Like everything you've learned about how to put a categorical predictor in the model, this is the same thing. Because from the perspective of the software, whether it's DV, A, and B, these are predictors. I'm thinking of them differently. I'm thinking of them as like outcome identifiers, but it's a semantic distinction. So the baseline for these models would be allowing each outcome to have a separate mean as a jumping off point, to not have to share a mean, because they're three different variables. So one way to set this up gives you the reference outcome as the intercept, and then the slopes represent the differences of the alternative outcome from the reference outcome. That's your standard dummy coding scheme. Here's an alternative. Actually, no, this is not an alternative. I didn't do that to you yet. This is adding a predictor, my bad. So if I add an X predictor, I add these terms to my model here. I have the effect of X as the beta 1, 0 slope here. And then I have X by the interaction terms with the DV identifiers. So by the rules of interactions, this slope of X, given that it's part of an interaction term, is for what specifically? If X is involved in these three terms, then X represents the slope of beta 1, 0 represents the slope of X for what specifically? Yeah, when everything else is 0, right? When you have slopes that are part of an interaction term, each main effect slope, simple main effect is the term that we use, each simple main effect is conditional on the interacting variables being 0. So when dVA and dVB would be 0 is when we're predicting a row that is for C. So the slope of X here is specifically predicting outcome C. And these interaction terms are saying how does the slope of X differ if I'm predicting A and if I'm predicting B instead. So if you had a hypothesis that, let's say some baseline covariate was going to be more related to one condition than the other, this is how you would test it. Differences in the effects of a predictor across repeated measures conditions. That's what this would give you. So I had an example that is on the syllabus that is from a previous class, because I'm not going to have time to do it, in which it was 2 outcomes, and it was the difference between ideal and actual body perceptions in college-age men and women. So the reason that I have these data was because I was helping a friend of mine answer reviewer 3, because what she had done is compute a difference score between your ideal body image and your actual body image. It was on a scale of like 0 to 10 with like these stick figures, and you had to say which one you look like and which one do you want to look like. And then she looked at whether gender predicted those difference scores. So were men more closer to their ideal in their perception than women, or something like that. So this is how I would set up the model if I were to try and predict ideal ratings and actual ratings at the same time. Because these effects of DV here, they carry the discrepancy. The body discrepancy between actual and ideal is captured by these slopes that differentiate one outcome from the other. So they are the difference scores that she was in search of. And her hypothesis was that there would be a bigger discrepancy in body image for men versus women. Women in particular, she thought would be more. That would be this interaction term right here. So X would be gender, and then the interaction of gender by the outcome difference would say the difference between these outcomes is a function of gender. So anybody who wants to do difference score analyses, these are the difference scores. They are model parameters straight up in here. So if the thing you care about is the difference between conditions, and you want to see if the difference between conditions is moderated by other stuff, this is how you would set it up. If this gives you a headache, anyone? Truth? Okay. Here's the code, by the way, how this would look. We'll see examples with this code. Here's the R code. I'm going to foreshadow. If this gives you a headache and you're like, oh my God, can I just predict each outcome? Yes. Here's the easier way to do it. Take out the general intercept. So you see beta 0 here is attached to a variable now. They're all attached to variables. So it changes the interpretation of each of these parameters without the general intercept. They are not differences. What they are outcome-specific terms. You can think of these DV, C, A, and B's as like light switches. They turn each term on and off. When it's that row, it turns on, because that dummy code is a 1. When it's not that row, it turns off. So what this is allowing is saying, okay, I'd like my fixed intercept for the outcome C, I'd like one for A, and I'd like one for B. That's it. Then when I add my slopes, I'd like the slope of X for C, I'd like it for A, and I'd like it for B. So it's a much more straightforward parameterization because each term is only operating on its one outcome, and the others are irrelevant for that purpose. Did you know that you're allowed to do this, that you can kick out the general intercept? I know, it's like craziness. In certain generalized models, it won't let you, but this is how path analysis works. It's like you're running multiple regression models for different outcomes at the same time. So you would get the same answers if you had a separate analysis for C, and then for A, and then for B, and you fit an empty model, and then you added the slope of X to each one. You would get the same answers. So ask me the question. If I get the same answers, if I do it one by one, why do it this way? What would be the purpose of putting them all together? The residuals, say more about that.
Like seeing the error in the model when you compare them together?
So at this point, each outcome would have its own type of error or its own like generalized model setup for it. So not quite, but I think I know where you might be going. Any other ideas? What if I want to know if X affects my 3 outcomes the same? Could I find that answer by doing it in 3 separate analyses? This picture. This is why. Separate analyses would answer, does X matter for A? Does it matter for B? Does it matter for C? Separate analyses can't easily tell me, does it matter more for B than A? So in dyadic data, this is a big deal to ask this type of question, what's known as actor-partner models, where usually you have like my outcome and your outcome and my predictor and your predictor, and you want to know if my predictor affects my outcome more than my predictor affects your outcome and vice versa. So then you get this like football sort of pattern with the slopes, actor-partner models. You have to have everybody in the model all together to answer those kinds of questions. So the reason to do this, even if what you're ending up with is just separate models that are estimated simultaneously, is to be able to make comparisons as to whether the means are different, whether the effects of slopes are different, whether there are differences in the amount of variability captured, or potentially to be able to have a common slope. So what if you did comparisons and X affects each of these three outcomes the same? Well, then maybe it makes sense for me to only have one slope and make them all share it. Then I can simplify the analysis. So it allows you to ask different types of questions that only are possible when everything's together. This I like better. Once you get your head around the fact that there's no intercept, then each of these belongs to its own thing, and it's a lot more straightforward. And if you want to know what the differences are between these fixed effects, those are just linear combinations with like a -1 and a 1, like you've done 8,000 times. Differences are linear combinations in that case.
What are you just saying, why we doing the, like, why we just putting them together is compared to why, like, because you wanna know, like, between each effect, are they compared to, like, if you separate three outcome, or are you compared to the previous one, the general intercept?
I'm not sure I follow your question yet. Keep talking, please.
No, I was just saying, like, you asked, like, why we want to put them together, right?
Mhm.
Like, so you are saying why we using this DV specific intercept, like, are you compare this one currently on the slide to the previous one when we have a general intercept?
Yeah, so the other way to do it with the general intercept, these are equivalent models. It's just a question of what you get directly and what shows up indirectly.
Okay, I see. Then, like, your says, why we using this is compared to the just separate outcome?
Yes, then that's a third possibility. So if you're doing a multivariate analysis, you can either set it up to emphasize differences between your outcomes as model parameters, or you can set it up to emphasize what happens to each outcome separately, and the differences are linear combinations. Those are equivalent. But where I was going was the rationale for if you end up with the same thing in terms of, like, the model would just give you the separate analyses all at once, why would you do that? And the answer would be to see if there are differences in the extent to which these slopes operate across outcomes, maybe to combine them, also to allow mediation, where you have multiple outcomes potentially. That would be another reason to do this within a path analysis type framework. So this is the concept of path analysis. In path analysis, we don't have to stack the data into one column. We just have separate columns, and we predict all of them at the same time. So this parameterization, I think, is much more intuitive. This parameterization also, by the way, can be used to rescue designs where something went wrong, like ANOVA with a hole in it. So I once had to help someone do this, where they had a longitudinal study where they had like time 1, 2, 3, and they had one cohort, and then they had another cohort, and it was like time 1, 2, and then they ran out of money. Oops. So if you picture like the cell means table, right, there's 3 columns and 2 rows, and then there's a hole right here. Well, if you wanted to look at like cohort by time and to see that the trends in terms of changing over time were the same across cohorts, you have a hole in it. You can't fit a classic ANOVA model with the main effective time, a main effective group, and the interaction because you've only got 5 cells. But what you can do is this kind of reparameterization, I would call it, to where you predict like each of the 5 separate means separately. Like you make a switch for each of the 5, and then you could contrast them in any way that you want. This is also useful for experimental designs in which there's a neutral condition that's sort of like separate. Like if you had something like looking at displays that are noisy, and there's different kinds of noise and amounts of noise, and then the comparative alternative would be like no noise of any kind, then there's no difference, like amount and kind doesn't make sense. You just have like the separate condition floating out here. You can use this type of parameterization to address that as well. So it shows up in a lot of different contexts for rescuing things that didn't turn out the way you planned. All right, 314. Anything else before we call it a day? It gets better, I promise. It does. Hang in there. I know, it's a lot. It's going to get better, I promise. Path analysis is super cool. That's where we're headed. All right, office hours are tomorrow as usual if you want to talk to me about your homeworks, which are due Monday night. So looking forward to seeing those. Thanks for being here. Bye, Zoomers, bye, Roomers.